Test. Yeah, perfect.
Hello, hello. Hello, hello. Good. You can't hear me? Okay.
Thanks. Just take this one. Should start. Okay. Hello, everyone. I'm Jose Marinho. I'm a system architect at ARM.
And I'm Zach Bobroff. I'm a product manager at AMI.
So today we're going to talk about secure system design on ARM using a platform root of trust. But first I wanted to call out that this presentation, or the core of the work, is really an attestation of PCI endpoints by platform root of trust. We'll still provide some details about basic building blocks for secure system design on ARM. That's just to frame the demo and to provide you a bit more context. So for a secure system, you first need to start with secure boot. And secure boot really starts the platform root of trust, where an immutable piece of firmware is going to load and authenticate the next mutable piece of firmware, which can potentially run on the PRoT. And then this mutable piece of firmware is going to load and authenticate the next firmware that may execute on a system control processor, such as the SCP, which is quite common on ARM platforms. And then the SCP is going to load and authenticate a more complex piece of firmware, and so on. Eventually, the firmware in the hosts is loaded and authenticated, the host is released, and the chain follows from there. And so you get the gist. There's a big chain of trust, but all of your security guarantees are anchored in the platform root of trust. So aside from secure boot, you also have the IO MMU, which is starting from a secure configuration, and by secure it means that any device that needs to sit behind the IO MMU is forbidden from accessing any system resources until you've established trust in these devices. Once trust has been established on the device, the entity that's responsible for controlling the IO MMU is going to open up the configuration, allowing these devices to access the resources that they should access if they're trusted. So the way a platform designer uses these building blocks is entirely implementation defined. This allows for flexibility, and it also allows for great innovation. But what you end up observing in the ecosystem is that partners are going to collaborate and create proven designs adhering to well-understood patterns, just like just like any other platform that you're accustomed to. So you have all the building blocks on ARM to create secure systems. And with a vibrant ecosystem, you may, or when you're a platform provider, you may need to integrate subsystems from different vendors. Say, for instance, systems that you may want to integrate in our platform are the BMC, or the satellite MC, and even the platform root of trust. And in order for you to reduce your time to market and reduce your costs, you need to have a well-defined interoperability story. In order for you to achieve this interoperability, you need standards, well-defined interfaces for the data model and for the physical layer and the way these different subsystems are going to communicate. To facilitate the interoperability story, ARM has introduced a server-based manageability requirements. This is a set of rules and design guidelines that will help you get all these different subsystems talking in a coherent manner. So on the right, you can see the different diagrams, or each diagram of SBMR of a particular level of compliance. It shows there the BMC, the server SOC, the satellite MC, and maybe I should call out that the satellite MC is very particular to SBMR. It's just trying to mediate the communication between the host SOC and the BMC to try to prevent any possible attack that the SOC may mount in its interaction with the BMC. So the use cases so far covered by SBMR are mainly on the manageability side, but we're increasingly looking at security use cases as well. A particularly interesting one is the platform root of trust and how it protects the non-volatile storage and the firmware store that lies within. But this is really just work in progress right now in the SBMR, but is going to evolve in the next coming weeks and months. Looking a bit more into the security use cases supported by SBMR, you have the platform root of trust performing measurement or authentication of the different devices, including the BMC. And device attestation can be performed at different system events, whether you have a firmware update of your endpoint device, you just perform a reset or just tweak the configuration in your endpoint. All of these activities may lead to changes in the security posture of your endpoint. And with a change in the security posture, the platform root of trust may want to reattest the device. And so there's going to be an event generated, and then the platform root of trust is going to be able to reattest and reestablish trust on this device. So similarly, this isn't just for endpoint devices. You can also have the satellite MC and the BMC needing some sort of mutual trust before they start collaborating in the functionality that they've been created for. And so SBMR is also going to introduce the notion of mutual authentication between these two privileged entities in the system. Another use case that SBMR is considering is how do you get measurements, whether from your endpoint devices or from your host firmware, externally via the Redfish out-of-bound interface, for either auditing or just for you to preserve the logs externally and consult them from the data center control. The last use case that SBMR is looking into, and the one that we've called out earlier, is how the platform root of trust manages and protects the firmware store. So an important aspect of the platform root of trust is that it can act as your root of trust for update. Whenever you have a firmware update, whether in-band or out-of-band, the platform root of trust, if it has control of the firmware store, can ensure that any image is authenticated before you perform any erase of the flash and trash any of the images contained within. So this is a protection role that the platform root of trust can take. Other roles can be more of a detection as well. So actively, the platform root of trust can go periodically, check the hashes of the different images contained in the firmware store to detect if any attack is ongoing. And if an attack is detected, the platform root of trust can bring the system into a known secure state. So this is a more active role, but all of these use cases are being considered in the SBMR and are being worked on as currently. So that's the background on the security building blocks on ARM, and now we're going to start discussing the actual demo that we've created. Here on the right, you see the different actors present in the demo. You have the hosts, the PCI endpoints, and the platform root of trust. The PCI endpoints and the hosts are communicating via the PCIe bus. The PRoT and the PCI endpoints communicate via I2C, and they exchange CMA SPDM messaging over MCTP. The CMA SPDM messaging is really what performs the authentication. Later on, the host communicates via secure channel with the PRoT to ask whether or not the PCI endpoints are authentic. On the left, you have the very high-level flow implemented in the demo. So on step 1, the PCI endpoints start by presenting all the different firmware measurements to the PRoT, as well as the certificates via CMA SPDM. On step 2, with all of this information, the platform root of trust is going to authenticate the certificates that it obtained, and it's going to check the different firmware measurements to determine whether they're known and trusted. On step number 3, the platform root of trust is going to determine whether it trusts the different PCI endpoints, and this brings us to step number 4, where later on, when the system has booted up until a particular point, the host is going to communicate with the PRoT in a secure channel and ask whether the different devices are trusted. And if they are, then the system just continues on booting normally.
Good. Thank you. So if we start talking about the demo, at the bottom there you can see the PRoT is going to attest the devices. It's going to do a component measurement and authentication. We utilize SPDM or security protocol data model to do a lot of this. We've got some details on it on the next slide. We'll go through that. And at the end of it, based upon either the authentication or failure of the device, we're going to do a security policy. The security policy we're using in the demo is very basic, but you can then expand it to much more advanced security policies depending upon your needs. Also, just as a note there at the bottom, the PRoT could be involved in more advanced TDISP flows. If we look at this on the right, the host and the PCIe endpoint, they talk over standard PCIe traffic. If you use TDISP, you could actually encrypt that traffic so that even if somebody was monitoring the bus, you couldn't even read the traffic or snoop on it and see what's going on. We didn't do that in this demo. It's also not entirely necessary because there's other protection against snooping, which we'll talk about in a second. So if we look here, this is a real CMA SPDM exchange. It's not every single step in the process, but it's the big highlights, and it's in fact most of them. This is intended to be pretty flexible. You could have the endpoint talking to the PRoT, you could have the endpoint talking to the host CPU, you could have the endpoint talking to the BMC, and then also the PRoT would be on the other side. Because as Jose talked about at the beginning, you want to have one certificate root of trust or certificate authority, which is in that certificate store on that earlier slide. And that basically means that any devices that are going to be authentic or authenticated need to be enrolled with their root certificate or their vendor certificate in the certificate store itself. So if you plug in a new device that's completely unknown, it's not going to authenticate no matter what. Also, this is a very flexible design. As we just talked about, you can have multiple different actors as the people authenticating devices all rolling back to your one platform root of trust or chain of trust from the beginning there. As well as just I talked about, if you're utilizing the BMC can provide all these reports up so that some external entity can be collecting all this information and monitoring what's going on data center wide. But if we just go through the flow here a little bit, it's very flexible for different versions. You might have something that's older playing with something new, so there's a lot of version checks at the beginning there so that we know what device version is supported. Also, it gets the capabilities so that we know what its capabilities are then. It then negotiates algorithms if it's an older device or if it's using one of the newest algorithms available. It then gets the measurements. So these are very similar to measurements you're familiar with in all other verification mechanisms. Maybe going back to authentic code, for example. It then actually gets the certificate so that it actually is saying, okay, this is one of the certificates I have. It's validating according to the measurements that I also know. And then this last step is that challenge. So this is what's really there to prevent against replay attacks. So a random number is generated and sent to it and basically then asked to re-encrypt it and send it back. So this challenge means that even if somebody's snooping on the line, they could provide all the initial data here, but they're going to fail this challenge at the bottom. So that challenge is this important step at the end there to verify that it is the device that's actually talking to me. If we take a look at the actual demo setup, as you can see, this is a normal engineering demo. We've basically taken a pre-existing system. It was an Ampere platform. And we have 2 cards that are plugged in, sitting right there. They're Broadcom storage cards. They're not the exact same card, but for all intents and purposes, you can consider them. One of them has a properly enrolled certificate. The other one does not. And that makes one of them attestable. The other one will have an invalid firmware. So as the system boots, the platform root of trust is going to go out and talk to these cards. And in fact, that's maybe another advantage or disadvantage, depending upon how you want to look at it, to how you wire this up. If the platform root of trust talks directly to the cards over I2C, it can actually do the authentication before enumeration even happens, right? So it can do this before the PCI bus is even going to be starting to be filled out, because that traffic over I2C is independent of everything else initializing in the platform. But at the same time, it means that you also still have to wait for the devices to come up. They're not up right away when system's powered on. The devices need to do their own powering on at the same time. But basically, depending upon your design, you can do this multiple ways. The PRoT, then, we talked about, has that communication. It attests them. And in the policy that we implemented here for this demo, if the device does not pass attestation or authentication, we halt the system. Obviously, that's not the most ideal situation for somebody. Maybe if you have a high security implementation, you would do that. But you could also just disable the device or eject the card from the platform at the same time. So this is entirely dependent upon how you want to go about doing this. But also, if we just go forward a little bit, you can see here is the part of the demo where we're reading the SPDM information. Again, pretty technical when it comes to the information you're seeing here, but it just shows you that if you wanted to audit what's going on the authentication mechanisms, there's the byte stream dump of everything that's going on. And at the bottom here, if we just click forward, it expands out, and you can see it's an invalid hardware detected. And as we mentioned, the system is going to be then held in reset, so that you would then see this and take the action that you needed to look at that bad device. If we look at the alternative case here, this device now passes authentication. And you can see the attestation succeeded, the system would release to boot, and the system continued to boot in that case. So while you may look at this being a complicated infrastructure for authenticating all devices in your system, it's very similar to other authentication and attestation you've done elsewhere. So you're just applying the same techniques and technologies here, and really just expanding the platform trust that you have in your system. So all in all, a pretty simple demo, even with the technical aspects behind it. If we look at the call to action, you can see the full demo video at our booth over at A15 if you want to come by and check it out. Obviously, Jose is going to talk about some more on System Ready, and you basically can see that a lot of authentication mechanisms you've used on other architectures other than ARM, you can replay or even expand in ARM architecture. So you don't need to reinvent the wheel here. You can take the same ideas and concepts you've used elsewhere and apply them to ARM, and ideally you can do the same things backwards as well. Obviously, talking about the ARM system architecture, I'll pass it back to Jose.
Yes, sure. Thanks, Zachary. So some aspects that we've described here today are parts or are part of the System Ready program. If you're interested in the JustWorks experience for system operating system install and boot, please try the System Ready certified platforms. If you're a platform vendor, consider certifying your platform. And if you're interested in contributing to SBMR or the ARM system architecture in general, consider joining the System Architecture Advisory Council ecosystem. And for that, you should contact Dongwei at ARM for the next steps. If you're interested in knowing more, please reach out to us. We can discuss offline or reach out over email as well.
Any questions?
You mentioned in the earlier slide that PRoT could interact with the TDISC flow. I'm curious what that would look like. Or if you have any more thoughts on that.
So we can definitely discuss that. One particular example is the PRoT acts as the certificate authority. So the PRoT is going to have the certificates that allow you to authenticate the certificates that you get in this CMA SPDM. So the host could conceivably ask the PRoT for the certificates that it may use to, in a TDISC flow, authenticate the certificates that it got from the endpoints. And so by this, you'd be mitigating a potential agent in the middle attack that could otherwise be mounted. I think that's the gist. But we can discuss this offline if you're interested in.
Yeah, basically we changed the flow from, in our example here, the hardware root of trust directly talking to the devices. The hardware root of trust would only really interact with the host for that initial certificate exchange, and everything else would go through the host in that case. Other questions? If we don't have any others and we have a minute, we do have the demo, that video that we can also bring up, but that's extra. Any other questions? I think I saw another hand. All right, should we drop into the video?
Yeah, definitely. I think
right.
that we should. Yeah.
So here you can see that same demo we looked at. There's the Mount Jade Ampere platform. At the bottom here, we've got the blue wired-in hardware root of platform root of trust board. It's a Mach-NX from Lattice in this case. We've got the two Broadcom cards here. It's going to directly call them out here what they are. This console we're reading, we basically put off of the Lattice card as it's pulling the information for everything that's going on. So it initializes the SBMR communication, basically starts talking to the card. This is about, I would say, available about 30 seconds after power is applied to the platform. It then is basically going to start pulling the information. It did those exchanges that we talked about, the version, the capabilities, so on and so forth, getting the certificates, getting the measurements, and then basically at the end here, it's going to then give you a either pass or fail based upon the information that's coming across. Also, if you click that certificate button, it basically gave you back the certificate. So if you wanted to inspect it, see if it was authentic, everything behind that. And if you click the measurements button, it also gives you the measurements behind it too. So by no means is this what you're going to see in the data center or in the field when you're doing this, but it allows it to simplify it for everything that you want to see. And in this case, you can see it was released to boot. It was an authentic one. And here we're just doing a comparison of the measurements here so that we can see that it was authentic too. And now we're doing it again where we switch to the NIC card as opposed to the RAID card. Initializing that SBMR communication again. We'll go through all the same flow and checks that we talked about here. Also, it doesn't take this long when you're actually doing it. It's obviously a lot faster. This is us utilizing the serial traffic and everything like that going on. And you can see here, this is where we got the failure, and the system's now held in reset. Again, looking at the certificate and the measurements, you can see that there are some issues now in this case. So, nothing too fancy, but exactly as it's supposed to operate. All right. Thank you.